That's to say Easter egg in the film sense, not Easter egg in the chocolate sense. Any of you aren't familiar with films and Easter eggs, once the credits have gone up, it's that bit at the end that the director wants to put there for people who wait. But since I know none of you will wait, I'll do it now. So the time before last, or perhaps last time as well, we spent quite a lot of time going over some transistor characteristics, and we had something like this broadly. Wow. And if this was a bipolar transistor, everything sort of here would be saturation, and all of this stuff would be either forward active or linear. But if it was a field effect transistor, I would have said that this was linear and this was called saturation, which is a thoroughly confusing situation to be in. So I'm more than happy for you to abandon that and think about a bipolar transistor and a field effect transistor in which this region is called switching and this region is called amplifying. Although if you talk to other people, there's a good chance they will go saturation, linear, and this, that, the next, and it would be nice if you could keep up. But if it's melting your brain, switching, amplifying works at bipolars and field effect transistors. If you want to know where the saturation bit comes from, there's a couple of pages in an appendix to Horowitz and Hill that spends a lot of time talking about transistor man, and it's a little bit childish, but it does get the point across. Right then. Anybody need some notes? Anybody not got notes? Anybody got spare notes at the back? Spare notes are there, right, okay. Good. There are some more there. Alrighty, well I suppose you better crack on. This is lecture 12, and in the last lecture we discussed an ideal switch and considered the non-idealities of a switch. And then we looked at three classes of switch, that was to say the mechanical switch, the electromechanical switch, and the electronic switch. And we spent some time considering how the switching action of the transistor is represented on the characteristics. That's to say, we drew a load line, we said, oh, there's 3 points, A, B and C, and it wants to spend a long time at A and a long time at C, but actually it can't get to A because the characteristics are curly, and that's what leads to the on-state power loss and the saturation voltage. And we did that through the idea of a load line. And we considered the on-state power dissipation, and I gave you some design equations for a MOS and a bipolar transistor. Some notes are behind you. And I said that this time we'd do a problem sheet style question. So we will. We'll do a switching transistor example, which is make a half-decent exam question, and then we'll talk a bit about how we deal with switching alternating currents, because we said right in the beginning that the conventional current will flow into the collector of an NPN transistor, and it will flow into the emitter of a PNP transistor. And similar arguments apply to field effect transistors. It will flow into the drain of an N-channel device and flow into the source of a P-channel device. So what happens if we want to do switching on circuits where we have sinusoidal signals? We could just use lots of transistors, but there are some cunning circuits we can use to get out of it. Then we'll discuss the H-bridge for a bit, which is a collection of 4 transistors that's often used to drive motors and generators. And then we'll round off this lecture by talking about how you switch inductive loads. That's to say, if you wanted to use a transistor to switch a relay or something similar, you'd have to worry about the energy that was stored in the relay coil and what happens to it, and we'll talk a bit about that. So this is, if you've had a look at the problem sheet that I gave out last time, this should be fairly familiar. It's question 1 but with different numbers more or less. So there's a circuit diagram on the right, and it says for the following bipolar transistor switching circuit, find, and then you may take the bullet points as 1, 2, 3 subsections of a question. Notice here. So find the collector current, find the load power, find the switch on-state power loss, the range of possible base currents, and the maximum value of RB. Right, they're listed in that order because that's the order that you do them in. If you want to do the maximum value of RB, you'll have to do the possible base currents first, and to do the possible base currents you'll need to have got the collector current. So there is no need to rearrange them. I have got you by the nose and led you through the question. So the parameters you need are supply voltage 48 volts, HFE for the transistor is in the range 35 to 170, the VCE saturation voltage 0.21 volts, VVE sats 0.7, and the input voltage to the base, VI, is 10 volts. And we can take that to be 10 volts pulse. But we don't have to worry about what happens before the pulse or what happens after the pulse. We can just say it's been 10 volts there for a very long time. Everybody happy with my description of the question? Is anyone uncertain what it's asking? Hear it again? Well, rewind from this point then. So, the solution. The on-state or saturation large signal model, which is on the slide, can be drawn if you find it necessary. I tend not to, and when I do solutions for this sheet, I don't spend too much time worrying about this. I tend to draw the transistor and then just put the relevant voltages around it without bothering to draw out the large signal model. It's more of a means to an end than something that you use all the time, because once you've got the hang of it, you'll find it just slows you down. But I've drawn it out here anyway so that we can have a look at the circuits. And the first thing the question asks us for is the collector current. So we'll apply Ohm's law to the collector circuit, and they've let me loose with a laser pointer, so I must have done something right. So collector circuit is, you're all going to die, that bit there. And it's entirely separate from, tell you what, I'll come over here, get a better shot of the target. So this is the collector circuit, and it's entirely separate from the base circuit. There is no way that current can flow from these 3 components towards these 3 components. And the reason is the only way that current can flow is, let's just say for the sake of argument, down through VBE, along ground, and then up through VCE. Fair enough. But how will it get back? There must be another mechanism for it to travel back. You can't have a circuit of just one wire. You have to have a loop for currents to flow in. So all this stuff can be ignored, and we only worry about this business here. In which case, for the current in RL, we've got a voltage on one end and a voltage on the other end. So we'll do that less that, divided by RL, gives us IC. So it's just applying Ohm's law on that bit. And for the numbers I gave, it's about 10 amps. When I'm setting exam questions, I like to make round numbers in the answers, because I don't think you should be penalised for numerical errors. But I will penalise you for numerical errors. So if you, well, I have to, I don't get a choice. If you get it wrong, I can't give you a mark. It's that simple. So if you're doing the questions and you find that the answer isn't a round number or nearly a round number, 1.004 kiloohms, that sort of thing, that's not an answer to this year's, but that order, if you don't think, yeah, that's a kiloohm, then you've probably made a mistake and you might want to go back and have another look if you've got time. You may judge that there is no point in going back and having another look, and you'd rather carry on and hope to pick up some more marks later on. That is your choice, and it's a piece of exam technique that you have to decide on the day. Anyway, back to this, about 10 amps. Next business is, what's the power in the load? So for the load power, we're only worried about this bit again, and we'll say, well, we can do V squared upon R, and we'll do 48 minus 0.21 squared upon 4.6, 4.6 being the load resistance, which is in the question. Yep, it's in the question, just there. And that will give us nearly 500 watts. So same logic, yeah, it's 500 watts. And then we can do the on-state power loss. Now you could, if you wished at this point, do 48 squared upon 4.6, and that would give you what would happen if you had a perfect transistor. Because you'd be saying there is no voltage dropped across the transistor, it is perfect, all the power is dissipated in the load, what would that be? And then subtract your 496.49 from that. If you want, that's fine. As it is, I've decided, I've got VCE sat, and I know what IC is, so I'll just multiply the two together, and I get 2.2 watts in my transistor. So this is 117 type stuff. It's still only a stone's throw from Ohm's law, really. Happy? Not happy. Confusing. Happy. Right, okay. So how about the base current? Well, there are two potential values for HFE, or rather, there is a range of values for HFE, but we will only be interested in the minimum and the maximum. And if we want to know about the minimum base current, we will have to deal with the maximum HFE, because that is the situation in which the transistor has the biggest ratio of collector current to base current. Collector current's fixed, we already worked it out. So if we want the smallest possible base current, we need the biggest ratio of IB to IC, so the biggest HFE. So if you want minimum IB, it's got to be maximum HFE. It trips a lot of people out, especially under pressure. Make some bad decision, even if you know what's right. It can happen. So we'll do IC is, IB is IC upon HFE maximum, and it's the HFE here has come from the question. I gave it on the slide where I defined what the question was, and it turns out to be about 60 milliamps. Conversely, for the maximum base current, you need the minimum transistor gain, so the smallest ratio between IC and IB, and that turns out to be about 300 milliamps. For the maximum permissible value of IB, you've got to use this is the one you're interested in, because you've got to allow the transistor to work, even if it's a really crummy transistor and has a terrible HFE. Has a terrible HFE. So you've got to make sure you can get this current in your base without any likelihood of your transistor switching off. So we'll do, if we go back to the, yeah, I'm going to pour that over the computer, put it down there. If we go back to the question for a minute, we've got V and RB and VB, so I would just draw VI minus VB across there. But if you don't feel up to that, you can go to the large signal model and you can say, well, I've got VI on this side, VB on this side. Same arguments apply as before as to why this side cannot interact with this side. You can consider them separately. So we do Ohm's law on RB, VI minus VB upon RB gives us IB, and that is just there. Yep. Not there, there. So yeah, VI minus VB sat on IB max will yield about 30 ohms. So you always assume the worst case. If you assume the best case, if you assume 61 milliamps, you'll end up with a much higher value resistor. And if you put that higher value resistor in your circuit and then try and run it and find it doesn't have the biggest HFE that you wanted, there will be too much voltage dropped across this bigger resistor to admit this current and still make the transistor switch on. And that's why it won't work. If you feel unhappy about that at the moment, have a go at a couple of questions, work it out the right way, and then work it out the way that you think it ought to go, and convince yourself the numbers don't add up, quite literally. And you'll be happy about it. I hope. So, an extra part to this question could go along the lines of, so that was part A for 4 marks or something. Part B could be, what would the new load power and transistor power be if the bipolar junction transistor was replaced with a MOSFET where RDS on is 1/8 of an ohm? So we have a new large signal model for our MOS transistor, and the difference now is that we have no voltage or no saturation voltage between the base and the gate and the source in this case, and we have no saturation voltage between the drain and the source. Instead, we've got a resistance RDS on, which you can pull off the data sheet. But as we said a couple of lectures ago, RDS on actually varies quite a lot with ID, but from the point of view of what we're about to do now, we will say there is one value of RDS on, and that is as far as we will take it. We won't have to worry about the fact that this can vary. Almost all transistor parameters vary, at the very least as a function of temperature, and eventually that will come and you have to deal with it. But for now, we don't have to worry about that sort of thing. So for the drain current, we'll apply Ohm's law to this bit here. The same arguments apply about the separation down the middle of the circuit. So now we've got one source and two resistances, so it's Vs is 48, 1/8 of an ohm is RDS on, and 4.6 ohms is the load resistance. So our new drain current is 10.1 amps. So the load power or the power in the load resistance, we'll apply the same equation we had before, V squared upon RL. And in this case it's just the two resistors, and we want just the power in this resistor. So we'll do V squared upon R for whatever VL is. So VL is Vs minus the voltage across this resistor here, which is RDS on times ID. So all the stuff in the bracket gives us VL, and it's squared upon RL. And if you pop the numbers in, it's not quite 500 watts. Happy? So, what about the power loss in the FET? Well, if we go back to the large signal FET model, what we really want to know is the power in this resistor, because this resistor represents the channel, or the resistance of the channel. So, we'll have to do I squared R, and we know what I is going to be because there's only one loop around here. You can consider this point and this point to be connected together. So there's a loop here in which ID flows that way, and we're interested in I squared R. Or if you want to, you could work out what VDS is, and then you can multiply it by ID, that would be fine too. So I'm doing I squared R, and its drain current, which is 10.158 amps times 1/8 of an ohm, gives us about 13 watts. So that could be part B, get you another 3 marks. Part C might say, what value of RDS on for the MOSFET would yield the same on-state power loss, insert the word power just there if you want to, as the bipolar junction transistor in part 1. So what I'm now saying is, what RDS on for the FET makes it just as bad as the bipolar, or just as good as the bipolar transistor, in terms of power dissipation. Obviously, we'd like to minimise the transistor power dissipation and maximise the low power dissipation. Or at the very least, we'd like to make the circuit as efficient as possible by making the load power significantly greater than the transistor power, and the end point of significantly greater is no transistor losses at all. So, using the bipolar junction transistor current and power loss figures, find an equivalent resistance. That's, when you read this, what the words you ought to see are this, because that is what you have to do to answer this question. You've got to go back to the bipolar junction transistor, get the current and the power loss, and figure out what resistor value in your large signal FET model, what do you have to adjust this to make the numbers the same as in the bipolar case. Dare I say that's all there is to it? Did I go the wrong way though? I did. So, for the bipolar transistor we had 2.2 watts more or less, and okay, it's IC for the bipolar transistor, but since this is still a FET we're talking about, it's ID. But this number is the bipolar transistor number for drain current. And we can say, well, we need a value for R, so we can do power upon I squared. So that's P is I squared R, but rearranged to get R. using the bipolar transistor numbers, pops out with 0.02 ohms. So considerably less than an eighth of an ohm. This was our RDS on from the FET part of the question, and this is the RDS on we need to make the FET power dissipation the same as the bipolar transistor power dissipation. And this is, you can find this sort of question on the problem sheets. Very, very similar, basically identical, but with different numbers. Happy with that or not? Happy enough for now. Righto. In that case, that is the end of that example, and we'll spend the next just under half an hour talking about switching AC signals. So the NPN bipolar and N-channel MOSFET can only really be operated with current flowing, conventional current flowing into their collector or drain, and the same applies to the P-channel except it's source and emitter. So conventional current into the emitter and conventional current into the source. What do we have to do to make it so that we don't end up trying to run a PNP transistor with conventional current flowing into its collector, which is the wrong way around? Well, the simplest possible case is just to add a diode, and this will only conduct when we've got more than 0.7 volts here bigger than there. So if you've got an AC signal driving your base, you can only have conduction of current down the page. Fair enough. The only trouble is that only provides half-wave rectification. And that means that essentially you're giving up half of your power dissipation in your load, which is certainly not ideal. It represents an efficiency loss of a half. So your best possible efficiency can now be a half, except it can't be because you've still got transistor dissipation and you've now got some extra dissipation in your diode, which is, if we say it's 0.7 volts across the diode, you've got 0.7 times IC dissipated in it. So you'll be lucky to get 45% efficient if you really try. So we can do a bit better than this. We could add another transistor. So no magic here, all that's happened is I've now got two diodes. So this bit, or rather that bit there, is the same as in the prior slide, except that I have now added a PNP transistor and D2, so that I will switch Q1 on in this will be time, this will be, you can either have it as V or I, it doesn't really matter, it looks the same. So I'll have some waveform like this, and D1 and Q1 will be doing with this bit, and D2 and Q2 will be doing with that bit. And you switch them alternately at just the right time and frequency to make sure that they each do the bit of conducting they're supposed to. I really need some sort of button to pull that back down, don't I? Look, I will give you a biscuit if you stay down. 2 biscuits? Come on. There we go. Is that enough? Right, good. Heaven knows how much that just cost the university for me to stand there doing that. So, everybody broadly happy with that? I want to hear it again. Everybody hated it so much they don't want to hear it again. Okay. The only other thing to say about this is if you need to, you've got to manage to get a non-ground reference driving signal here, because this has to be 0.7 volts below that. If all your driver circuitry is with respect to 0 volts, you need to concoct some funny circuit to make your drive signal for Q2 with respect to the anode of the diode, which is not easy, but in practice it's not so difficult either. So we can do a bit better because we have 2 transistors in the prior circuit and we can actually get it down to 1 by using a bridge rectifier. And we will manage to get only conduction down the page, down here, in that direction. And we'll arrange that by, because this is still a signal like that was, of two halves. The first half of things will be like this, and we'll have current flowing. So this is now the right way around this arrow. So this is more positive than that, and we'll have current flowing up there, along there, through this diode, which is forward biased, down through the transistor, through this also forward biased diode, down there, through R from our right to our left, and then back into the source. And as an exercise or fun or something to get you to sleep at night, if nothing else, well, you can prove to yourself that D2 and D3 are reverse biased. For the other half cycle, so the second bit of that graph, we have VS has changed direction, and we've got current flowing from our left to our right, which is the opposite of what we had before, which was from our right to our left. So we have AC current in the load, but we have DC current in the transistor. We have current flowing through the load, left to right, up the page, along here, through this now D2 forward bias diode, downwards through the transistor, which is the same as before, through D3, which is forward biased, and back into the source. And you can also show that D1 and D4 are reverse biased in this situation. So this eye here, always down the page, this eye here flips backwards and forth according to input signal. There we go. Right, quite enough fun. Happy with that? I'm happy with it. Happy with it, good. There really isn't very much opportunity for biscuits today. I don't know why, it's just some lectures go like that. So we can talk about H-bridge as well. Oftentimes we use these for motor control. And by motor control I mean the motor is in here, and we have some situation whereby we want to drive the motor either forwards or backwards. And I'm not too worried about universal machine, DC machine, brushed, unbrushed, switch reluctance, induction, doesn't matter. Any old machine, okay. Any old single phase machine. So we have 4 switches arranged in a H, and the middle of the H is the load. And just by way of example, you will not find this in a Toyota Prius. You'll find something like it, but quite a bit more involved. But it really all boils down to this sort of thing. And it just so happens that for the battery pack they've got, it's about 220 volts and about 110 amps when it's going flat out. And that's either 110 amps from wheels through generator into battery, or 110 amps out of battery through motor into wheels. Depends if you're slowing down, speeding up. And by controlling the switches, that's Q1, Q2, Q3 and Q4, you can adjust how the current flows by what amount and in what direction. You can even switch Q1, Q2, Q3 and Q4 very quickly to arrange it so that the average current is lower, but the peak current is very high. And you might want to do that because it gives you some control over the torque that the machine develops. The torque is proportional to current times some stuff, and some stuff depends on what kind of motor it is. So if you want really high torque, but you don't want too much in the way of speed, you can pulse width modulate your machine currents to give you really high peak torques and a high average torque, but an overall speed which is quite low. That will, don't worry about that for now. If you don't like the sound of it, it will come back in second year, I would have thought. Certainly you don't need to know it for this. Anyway, we can run this motor in both directions, and we can control the average power. So if both A and B are on, so I've arranged an A and a B and a B, and we'll switch the transistors in pairs. So Q1 and Q4 will switch together, and Q3 and Q2 will switch together. And the situation in red, which is on the left, is A is on, B is off. And the situation on the right, which is in blue, is B is on and A is off. There is the possibility that you could switch A and B on together, and a very large current would flow from your V supply down into your ground and destroy your switches, probably, unless you're very quick to shut it off. There are actually 6 situations of this circuit, but I only really want to discuss 4 of them because the other 2 are really meant only for machine type situations, and since we are going to discuss machines, it doesn't make a lot of sense to spend a lot of time running through them, but I may talk about them anyway. So as far as we're concerned, there are 4 interesting states. So machines are usually inductive loads, and so are relays. And relays are something that we have to talk about in this course, so we need to talk about inductive loads a bit, even if we're not too worried about machines. The principal difficulty here is we've got this inductance and some resistance, which is our load, and a switch, which is ideal. And we have this point A, which is the connection between the end of the inductor and the start of the switch. Now, the inductor could be the coil of a relay, or it could be a machine. It doesn't make any difference. It's essentially the same thing as far as the circuit is concerned. It's an inductance either formed around a piece of soft iron whose job is to actuate another piece of metal, or it's an inductance formed around a piece of soft iron whose job is to induce a magnetic field in another piece of soft iron to cause a rotation or a linear motion. Whatever way it goes, it's the same sort of thing. You could even say that a linear motor is a relay, because what's happening is you've got an electromagnet which is pulling something back and to, which is just the same as a railgun, where you've got a long electromagnet that fires a bullet or some other projectile, or a train if it's a maglev type thing. They're all linear motors, so there is really a big blurring between, is a relay an electromechanical switch, or is it just another kind of electrical machine? So anyway, we've got this inductance, and it doesn't really matter how we acquired it, and we can write some things down based on the sort of basic laws that we know about inductors and capacitors. And we can say that the voltage, or we could say that the inductor will try and keep the current flowing. So if I have a current flowing in L1 and R1, and I open the switch, this inductor will have a magnetic field surrounding it, which contains the energy that's stored in it according to half Li squared. And that energy will leave because the magnetic field is sustained by the current that's flowing. So we have this energy which is guaranteed to go somewhere because the magnetic field will collapse. And the energy that we have will emerge in our circuit in such a way as to attempt to keep the current flowing which previously sustained it. If anything else happened then, we would be breaking some thermodynamics up, and it wouldn't make much sense. So the energy which is here will leave this inductor, and in so doing will attempt to keep the current flowing. When we actually open the switch, we've got di by dt in this pathway of infinite, because we suddenly open the switch and all of a sudden the current stops, and we'll assume that it stops immediately because it makes everything else that follows a bit easier. If that happens, we can apply V is L di by dt for the inductor, so there'll be a voltage generated across the inductor by this sudden di by dt of L times di by dt. But this is infinite, so V ought to be infinite as well. Happy? Unhappy. So I had some current down here, and I open the switch, I switch off the current, say it switches off in a really short period of time. I can apply V is L by di by dt for the inductor voltage, and if I say that the current switching off event was 10 picoseconds, say, pretty unlikely, but that's quite a small amount of time. It doesn't really matter what L is going to be or what I is going to be, as long as I is reasonable. Say it was an amp, and I had a 10 picoamp switch off time, and L was 1 Henry, just for the sake of argument, that would give me as V, which is rather a lot. So the smaller I make the T, the bigger the V will be, and it doesn't really matter too much about the L and the I as long as they're not zero. Alternatively, you could say I'm going to switch 10 megaamps in a millisecond, that will give you a really big voltage too, irrespective of the value of L, as long as it's not 0. And the final one of those is if L was huge and I and T were both quite small. You can get a big number any old way you like just by choosing your values accordingly. T has to be small because it's on the bottom, L and I have to be reasonable because they're on the top. So we've arrived at this large voltage across L, which is attempting to keep the current flowing. And as the magnetic field collapses, it causes a current to flow towards A, or it wants a current, well, it doesn't want. Let's pretend it has feelings and it wants a current to flow towards A. Now the current can't actually flow because there is no closed circuit for the current to flow in, but there is some energy which was stored in the magnetic field and it has to get out somehow. And it's going to make some attempt at doing that by increasing the value of the voltage across the inductor in order to try and keep the current going. So we have this charge which has to leave, and if it comes out to A, or say the energy sort of goes down here and it's in this small region between the inductor and the switch, it's got nowhere else to go after that. So we need to figure out what's going to happen to it. It can't just sit there on that node. That is not allowed. You can't have energy just sat in your circuit doing nothing. Unless, of course, it's sat in a battery, I suppose. So we can say that the node A has got some stray parasitic capacitance, however small that may be, due to its physical dimensions. So if I built a real circuit with a real inductor and a real switch and so forth, there would be a small amount of capacitance between all the wires and all the ground wires. And if it was on a circuit board, the printed circuit board would probably have a ground plane, and there'd be some parasitic capacitance between the PCB tracks that I was interested in and the ground plane that surrounded it. One way or another, there will be some capacitance. If I wore a really shiny metal suit and you wore a really shiny metal suit, in the front row there would be a couple of femtofarads of capacitance between our two surfaces, because I would be an insulator and you would be an insulator, and there would be some air in between us, which would be an insulator. Sorry, I would be a conductor and you would be a conductor, and there would be some air between us, which would be an insulator. And a jolly good thing too. So there is some charge which is going to come out of this inductor, and it's going to arrive at node A, and there will be some small unknown parasitic capacitance that we're not clear on. And we can say, well, we know that there will be some charge Q, and we know that for a capacitor Q is CV. Since C is quite small, V must become very, very large to accommodate even a small amount of Q. Small amount of charge, tiny little capacitor, big voltage required, because it's volts per meter for our electric field, and the electric field is going to have to be substantial to store up a large charge, or even quite a small charge actually. So we will end up with a very, very large voltage developed across L1, and the charge that's leaving this, or the charge that is resulting from L, due to the collapse of the magnetic field that surrounds it, will end up charging up a parasitic capacitance around the node A, and that energy that was formerly stored in the magnetic field will become stored in the electric field of the capacitance. Okay? What will happen then? Well, then will have been a very big voltage across the inductor, and that voltage is very likely going to be bigger than the breakdown voltage of our transistor. So when that voltage appears, our transistor will break down, the current will flow, and the transistor will die. Or at the very least, will sustain, okay, it might not sustain any damage at all, but the chances are its life will be shortened, generally. You certainly wouldn't, if you were rating something for 20 years, you wouldn't allow your turn-off spikes to go unchecked. If it's only got to last for 10 minutes for a quick demonstration because the managing director's coming around and needs to see it, well, they need to see it, maybe you won't care because you're going to throw it away in 25 minutes. I suppose it depends a bit, but for good design, the situation is high voltages might occur on A as we switch off the inductance, as we switch off the current in the inductance, and the solution is to provide another pathway. And actually A could be really, really huge. It can get up to sort of 10-15 kilovolts without really breaking a sweat, especially if the current's big and the inductor's big, the switching time is short, and the parasitics on A are tiny. That's the situation that gives you big voltage spikes. So we can, if we say A is going to get above Vs for a very short period of time in terms of voltage, we could put a diode in reverse bias from Vs to A. So all the time that A is less than Vs, no current will flow in the diode. But if A suddenly jumps to more than Vs by 0.7 volts, or whatever our diode terminal voltage is, this node, anode, will be higher than cathode, and the charge that leaves the inductance will not charge up a parasitic capacitance on A. It will instead turn on this diode and flow back into the supply, quite harmlessly. And then the maximum voltage on A will be whatever we had, it will be Vs plus 0.7. And as long as Vs is safe for A to experience, our circuit's going to be fine. So that's what I've said in the bottom bullet point there. It's the diode is reverse biased under normal circumstances, and if A is more than Vs plus 0.7, the diode will conduct any charge on A back into the power supply. I fully expect that you're all sitting there going, nope, what are you talking about? Don't panic. It's not easy because one of the key components in this circuit isn't even drawn on the diagram, and that's to illustrate the fact that it's not something you're in control of. Have a bit of a think about it in about 2 or 3 days' time once you've slept on it, and if you still don't get it, go through the logic again, and if not, come and see me. The reason we need to deal with this is because when we deal with the machine or inductors in the H-bridge, we have to worry about where these currents are going to go, and it will be more than one diode that's dealing with this voltage spike and the current that results from it. For the single situation we've got in the slide above, that one there, we can say just after the switch off event, so A is just opened, the diode current is equal to the on-state inductor current. That's to say there was some current flowing in the inductor and it was flowing through the switch, and now it can't flow through the switch anymore. That current will keep going, and it will keep going because the energy in the magnetic field surrounding the inductor is leaving the inductor, leaving that magnetic field, so the field is collapsing, and the energy that was there is now a charge which is flowing in the circuit, and it's flowing through the diode back into the power supply. After the switch off occurs, this current falls exponentially with a time constant of L1 upon RT, where RT is the total resistance in this loop here. So there'll be some, when you switch off, there is a current that flows down here. As you open the switch, that current changes to flowing in this loop here. And there will be an exponential decay because we've got an L and an R, so we'll have a first order circuit of that current, and all the voltage that surround it, or will make it go, will decay as an exponential according to the same sort of laws that deal with RC networks. You could, if you want to put an extra resistance in series with the diode, to actually adjust the time constant, and you might want to do that if you've got to pass some sort of EMC specifications. And some of the questions in the problem sheets do have a resistor there, and others don't. So in some applications, this inductive kick is desirable. So certain types of switching converter will make use of this property of getting a current flowing in an inductor and suddenly opening the circuit and then catching that voltage somewhere else, or the charge which goes along with it in another circuit, and using it to change one DC voltage into another. And you can see some more about that in EEE118 something or other, because they've changed the course and I can't remember what it was. But I did change it in the last set of lecture notes, so a couple of lectures back I said there's 2 courses that are involved in this sort of thing in 2nd and 3rd year. If you want to know about them, they're in there. The other thing you can do with this is if you need really high voltages for CRTs. Now CRTs are pretty unpopular at the minute, full of horrible things like lead and mercury. Also they're big and heavy and cost a lot to produce and can't be recycled, and all the usual complaints. On the other hand, there are some situations that you really can't do without them, and I don't mean tellies and that sort of thing, scientific applications that require them. So they are still used quite a lot actually, although consumers don't see them nearly as much as they did 5 years ago. The other thing you can do with them is, the point of them there is to make the big voltage that drives the electrons towards the phosphor screen. Something else you can do with them is internal combustion older IC engines where you had a mechanical distributor. The spark plug is an inductor, and the distributor is, or was, a series of mechanical switches driven by a motor, and what happened was the switch blade just went round across the 4 contacts if it was a 4-cylinder engine, and it would cause the inductive kit to jump across the spark gap and ignite the fuel air mixture in the cylinder. You don't use distributors like that anymore, they wear out really quickly. It's all done by an ECU, and the switching's done electronically now, and variable valve time and all that sort of thing. But it is the same effect, and it did work very nicely from the invention of the motor car to about, I don't know, 1990-ish, so we got 90-something years out of mechanical distributors. So the energy that's stored in the inductor drives the back EMF process, and the situation is similar for electrical machines. And it's electrical machines that I want to talk about in H-bridges for a bit now. So this is the bridge that I showed you earlier, except that I've got 4 diodes in it as well now, and I've got an inductance and a resistance in series. And the inductor and resistor in series could be a relay, or it could be an electrical machine, or whatever. The operation is similar to the prior situation. We've got A on and A on, or B on and B on, but the energy in the inductor has to be able to escape back to the power supply, and if it can't, we'll end up with big voltages everywhere. And that could destroy some of our transistors, and that would obviously not be desirable. So as soon as the switches turn off, whichever ones are on, as soon as they turn off, the inductor current has to be the same. That's the key first assumption, is at the moment of switch off, the current in LL has to be whatever it was just before switch off. And then the diodes will have to turn on appropriately. That's to say, the ones that get forward biased will turn on, the ones that get reverse biased won't, to conduct that current back into VS. And there are 6 interesting states, but we will only deal with 4 of them. And we can rifle through them pretty quickly because they're all coloured in. And I know you haven't got coloured in notes, but if you download them from the teaching resources, they are in colour. So a current flows out of the supply through A, through the load, from right to left, through the other A switch and back into the supply. So this could be motor is spinning clockwise, for example. And we'll assume that IA is constant and the A switches have been on for a long time, so we're not worried about any exponentials that we might get due to the machine spinning up or anything like that. We'll say that it's been running for ages. So the machine is drawing electrical power from the supply and converting it into mechanical power. That's to say, energy leaves our chemical energy source and ends up as rotational energy, described by the inductance. So the A switches have been on for a long time. So the situation in red in the prior slide has been existing for a long time, and suddenly we switch off the A switches. So the current that's in LL has to keep going, and the voltage that's produced by the collapsing magnetic field around LL will be in such a direction as to maintain the flow of current. So if you were to look at these 2 arrows, there isn't time for a biscuit, but this arrow looks like it's the wrong way round. Right back in lecture 1 I said generators have their voltage and current in the same direction, and dissipators have their voltage and current in opposite directions. Well, an imperfect inductor is a dissipator, and this one's got its voltage and current in the same direction. So this one is giving up energy into our circuit. This is the source of energy, and it's driving our chemical energy source. And to make that happen, D3 and D2 have switched on, they've become forward biased, and the current will flow in this pathway until the energy in the inductor has been diminished. And no large voltage will have appeared here or here. Similar arguments apply to the situation where the B switches have been on for a long time. We have B and B are on. A current now flows through the machine in the other direction. So this could be machine rotating anti-clockwise. And there is a constant current flowing in the machine, so it's spinning at a constant speed. And this is electrical energy here converted into mechanical energy there. Once the B switches have been on for a long time, we switch them on all of a sudden. A voltage appears across the inductor in such a way as to maintain that flow of current. D1 and D4 become forward biased, and that current flows back into BS, and the energy inside the inductor, which was formerly stored in its magnetic field, is diminished, and no large voltages appear here or here. So in this situation, the motor is now a generator. So today I started off with a switching circuit example in the style of a problem sheet or exam, and we considered several transistor switching circuits for AC systems, including a half wave, full wave, and a bridge. And then we talked a bit for H bridges, about H bridges without any diodes or inductors, and then I spent a bit of time going through a really strange middle section which killed the film dead, where we talked about energy inductors and so forth. And then we applied diodes to our switching circuits in such a way that the energy stored in the inductor would not upset the circuit or destroy the transistor. And then we applied that same approach that we used with diodes to a H bridge to show how the energy that's stored in a rotating machine or an inductor with a current in it can get back into the supply without damaging the driving circuitry. Righty, I suspect next time we're on to amplifiers, so this is all you'll get from me on switching. So feel free to have a crack at the switching transistors problem sheet if you wish.